In this video, I'm going to show you the difference between an empirical and a molecular formula. When you study the composition of chemicals, you're going to need to know a little bit about both of these. So let's get started. I want you to think about these two compounds to begin with. Sodium chloride is actually an ionic compound, and here's what it looks like. There's one sodium ion and one chloride ion in that compound. The chloride's this green ion, the sodium is this gray colored ion. Look at the second compound. This is a molecule of hydrogen peroxide, like what you buy in the grocery store, the drugstore. Hydrogen peroxide's formula is H2O2. So look at this molecule. This molecule is made up of two oxygen atoms, represented by the red circles here, and then two hydrogen atoms, which are represented by the two white circles on the ends. Now you'll notice that the ratios here are different. An empirical formula is the lowest ratio of atoms, and that's what the sodium chloride shows us. In a crystal of salt, there are millions and millions of sodium and chloride ions. But the ratio of sodium to chloride in salt is 1:1. That's the empirical formula of that compound. The molecular formula, however, is the true formula, and that's demonstrated in the hydrogen peroxide. You see that the true formula for peroxide is H2O2. However, when you're considering the ratio of hydrogens to oxygens, the smallest amount, the lowest ratio, in other words, is really only 1:1. The true formula is H2O2, but I could divide that by 2 and get a reduced empirical formula for hydrogen peroxide of HO. So that's the main difference. MPO are reduced. Molecular is not reduced. It's a true ratio. Let's look at some more examples. I want you to write the empirical formula for each one of these compounds. Now what I want you to do is pause the video here, and I want you to go through each one of these and think about reducing them. Can you take each of the subscripts for each element in the compound and divide it by a number so that you get a lower ratio of atoms? So pause the video here and write your answers on your notes, and when you're done, I'll show you my answers. Okay, you have your answers ready? Here are mine. The first compound, propene, C3H6, you can divide by 3. So if we go through and divide C3H6, divide all of those by 3, you end up with C1H2. So that empirical formula is going to be CH2. Now for the second compound, ethene, C2H2, you could divide each one of those by 2, and you get C1H1. The glucose, you could divide each one of these subscripts by the number 6, and you'll get C1H2O1. Remember, those ones are understood. And then finally, octane, like in gasoline, you can divide by, if we divide by 2, I think that's going to give us the lowest ratio. We get C4H7. You can't reduce that any further. So it's like dividing by the greatest common factor in math and getting the lowest ratio possible. Now in this slide, what I want you to do is to decide if each one of these formulas is an empirical formula, a molecular formula, or could it represent both. We want to do the same thing. Pause the video, and when you've made your choices, hit play again, and I'll share my answers with you. Okay, now that you've gotten your answers, let's compare. The first formula, H2O, actually represents both an empirical and a molecular formula. The compound, of course, is water, so you know that that's its true formula, but because it can't be reduced anymore, it's also the empirical formula. The second compound is a molecular formula. because you recognize you could divide both of those by 2 and get a reduced version. So this must be the molecular formula. This is actually the formula for butane, like the liquid that's in the little Bic lighters. The third formula is an empirical formula. CH represents a 1-to-1 ratio of carbon to hydrogen, but this is not an actual compound, so it represents only the empirical ratio, the lowest ratio of atoms in a compound. And finally, the last one, NaCl. This represents both. NaCl is the true formula for sodium chloride, or table salt, but it can't be reduced any further than it already is, so this represents its empirical formula as well. So I hope that makes sense, being able to simply recognize by sight an empirical formula or a molecular formula. Now let's look at how to calculate them. You already have these steps in your notes. What we're going to do is we'll be given the percent composition of a sample, and we're going to convert that to grams. Then we'll convert grams to moles. We'll divide each one by the smallest, and if necessary, because sometimes it is, we'll have to multiply by a number to get rid of a decimal. Finally, we'll conclude by getting the empirical formula for the compound. The little poem that's over here on the left that may help you remember is percent to mass, mass to moles, divide by small, multiply till whole. That's just a little poem that'll help you remember these 5 steps. So let's take a look at an example problem. In this problem, they give us the percent nitrogen and the percent oxygen in a compound. So I'm going to start out changing those percents to grams. Now this is really easy because if we assume a 100-gram sample, 25.9% of nitrogen is 25.9 grams of nitrogen. And similarly, 74.1% of oxygen is 74.1 grams of oxygen. The percentage is the number of grams if you assume a 100-gram sample. Now the second step was to convert mass to moles. So I'm going to go to the periodic table and I'm going to set up a conversion factor where my grams of nitrogen cancels and I get moles. Now I know that in 1 mole of nitrogen the mass is 14 grams. And I'm going to do the exact same thing with oxygen. 1 mole of oxygen here has a mass of 16 grams from the periodic table. Grams of oxygen cancels and grams of nitrogen cancels. So let's grab the calculators and do that math. I'm going to say 25.9 typed in my calculator, divide by 14 grams. That gives me 1.85. Now I would recommend that you leave a few decimal places in this instance. I don't want you to round off a whole lot here because it could mess you up later. So I'm going to have 1.85 moles of nitrogen for that one. In the second one, I'm going to divide 74.1 by 16 grams, and I get, for that one, 4.63 moles of oxygen. Alright, so now I've converted my grams to moles. The next thing I need to do is divide by the smallest. Whenever you do these problems, you're going to look at these 2 mole answers. You are going to divide all of them by the smallest answer, which is 1.85. 1.85 is smaller than 4.63, and that's how I know what I'm dividing by. So this one, of course, is going to give me, I'm going to put a big arrow down here so you can follow. I get 1 mole of nitrogen. When I divide 4.63 by 1.85, I get 2.5 roughly. Now I know there's a lot of decimals, but it's pretty close to 2.5 moles of oxygen. Now this would be the subscripts for the formula. It would be N1O 2.5, but you can't have a subscript with a decimal in it. So what you have to do is think back to all the math that you've learned. How do you get rid of a half in a number? Well, the answer is to multiply by 2. If I multiply 2.5 by 2, I'm going to get 5 oxygens. if I multiply the oxygen by 2, I also have to multiply the nitrogen by 2. So 1 times 2 gives me 2 nitrogens. And now that I've got whole numbers, I can write the empirical formula for this sample. It's going to be N2O5. The ratio of nitrogen to oxygen is N2O5. For every 2 nitrogens, there are 5 oxygens. The true identity, or the molecular formula of the compound, you would need a little more information to figure out. So I hope that helps. We'll work plenty more next time we're together. Have a great day.